right, time for parametric equations part 2. Anyway, so yes, I did make another video, and this would have been the first slide in that video. And just in case you're not watching these consecutively, then what I said was about this was that in parametric equations, x and y will be functions of some third thing called t. T is the parameter, all right? If you want an analogy to this, then you can think of it like an object is moving in two-dimensional space if you have x and y is the place, and t is the time, and if something's moving, then at any time it has to be in some place. You get concepts like the path that the object is moving along, the direction it's moving, and how fast it's going, okay? So that's basic, with some algebra and other details. That's the main idea of the last video. In this one, I just wanted to do some other examples, okay? All right, so let's take this one, new set of parametric equations, all right? X is 3 cosine 2t, y is 3 sine of 2t, for t running from 0 to pi over 2. And I had the same outline that I had before, where I'd like to sketch the graph, indicate the direction, okay? And then give an equation for the path. All right, so those are the initial concepts with parametric equations. So here I decided I'll go ahead and make the table out ahead of time. If you let t run from 0 to pi over 2, then I could choose numbers like this as sample points to get a graph. If I'm going to draw a graph with a table, I just need some sample points. All right, so I decided I'd count by pi over 8. All right, 0, 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, okay? And then I did the math, all right? Where did I get these numbers? Where did I get x and y? Well, if t is 0, x is 3 cosine 2 times 0. That's 3. And if t is 0, I get y to be 3 sine 2 times 0. So that's just what you get if you put that value of t up there and getting x and y. So same thing with the others. Now, these points, like if I sketched them, I think it would be kind of hard to see a real good pattern. So I'm going to put this part on hold. Okay, I think this one, it's a little hard to figure out the graph from just the points. If I have the path, what's the path? That's an equation in x and y that tells me how the object is moving. All right. If I can get that, then I'll know the overall pattern of those points. Like in the example that we did in the last video, I wanted to figure out what the graph looked like, and I had 3 points. And, maybe 3 points is not definitive as far as a pattern goes. But if I tell you, oh, those 3 points come from this graph, and that graph is a line, then that is definitive that the path is linear, that the path that this object moves along is a line, okay? So that's how the two of those things interact with each other. So let's put a hold on this, okay? And let's do this part. All right, so let me go ahead and I'll write everything down after making some adjustments. All right, so here's what I'm working with this time. X is 3 cosine 2t. Okay, and y is 3 sine 2t. Now, as I write that down, I remember that before, like say in my other video, when we had found the path, it was just algebra. You solve one equation for t, then you sub it into the other one, and t is gone, and you get just something in x and y, and that's what the path is. But I don't really think the algebra is the way to go with this one, okay? So something that I see, or that I think of when I see sine and cosine, are identities. Specifically this one. I've got sine squared of angle theta plus cosine squared of the same angle theta is 1, okay? And I feel like that is going to come into play in eliminating t and getting just an equation in x and y. Remember, to find the path, the entire objective is to eliminate t, okay? All right, now what's this say? It says, well, with as far as angles go in sine and cosine, sine squared of an angle plus cosine squared of the same angle is always 1. That's why I think we can use that. Okay, so look at this. Say I do like so. Say I divide both sides by 3. In that first equation, I'll get x over 3 is cosine 2t. In that second equation, I'll get y over 3 is sine of 2t, right? Okay. And then now say that with the objective of using this at some point, I'll take these equations and I'll square both sides. Okay. Then here's what I'll get. I'll get x squared over 9 is equal to cosine squared 2t. And y squared over 9 is equal to sine squared 2t. Okay, now look at it like this. What does cosine squared 2t and sine squared 2t add to? It adds to 1. Because sine squared of an angle or something plus cosine squared of that same angle or that same something is going to be 1. So this and that add up to be 1. This plus this is 1. Oh, well, looking at the other sides then. This plus this, also 1. So we'll get x squared over 9 plus y squared over 9 equals 1. And then if I multiply this by 9, I'll get finally something that I think is some standard equation that I can recognize. If I multiply all that through by 9, I'll get this. So what is that? That's the path, okay? See all these points? See all these times and places? This represents movement of something. Its movement is along that. That's a circle that has a radius of 3, and it has a center at the origin. All right, so there's our path. It's circle. Okay, the path is circular. Its radius 3 because that's a 9, and the center point is the origin. All right, so that'll explain these in a whole new light. All right, now I'm going to pause it. I'm going to sketch that graph, and I'm going to overlay these points. All right, it turns out it's semicircular. Okay. All right, so here we are on the XY plane. Right here, that's 3 for x, 0 for y. Say my scale is 1, 2, 3. 3, 0, that's when you have t to be 0. Then this other point, that's like 2.1 and 2.1. Okay, that's going to be over there somewhere. But let me graph the ones that'll be easy. Like that one right there at the top there, that's this one. That's going to be 0 for x, 3 for y. That's for t is equal to pi over 4. And then this one, that's going to be left 2.1, up 2.1. That's going to be like about right there. Okay, but then this nice round number there, negative 3, 0, that's this point, okay? So negative 3 and 0, we're there when t is equal to pi over 2. All right, so that's, if I had just plotted these points, they would have gone like this, okay? And if I didn't know that the path was actually circular, I mean, who knows, what path do you take to get from this point to this point to this point to this point? It doesn't have to be a circle. These are just points. These are just places. If this is all I have, that wouldn't prove that it was circular, okay? So I guess the only way to definitively know the path of the motion is to do this, to eliminate t and figure out what you get in x and y, okay? So, all right, given that t is restricted between 0 and pi over 2, this is the beginning, that's the end. All the points in between are circular, a semicircle in this case, okay? All right, so I'll say with that, I'll put my direction like this, okay? And I like to put everything in one spot, so I'll say circular path by equation x squared plus y squared is equal to 9. And you see the 3 and the 3 suggest circular path radius 3. Okay, that's according to that equation. But really semicircular. Okay, all right. So that's how we can do that one. I think this part might be a little bit tricky if you didn't know how to address it. But if I see anything parametric with sine and cosine, that's the identity that's probably going to be in play. Okay? All right. So we got that one. Now, let's do two together that have some similarity between them. And then I'll say, like, I'll give a little bit of fine print about this last one. Okay? All right, so this one. So it says, give parametric equations for the object that's at point -1, 4 when t is equal to 0, and then it moves in the direction of 4 and -3. So let's think about that. I think for this one, I should probably start with a picture, and I'll tell you why I think that is once I get the picture there. I know we're starting over here. Now, I'm not going to draw this to scale, okay? But we're here, okay? And we move towards this other point that might be like right there, okay? So we're here, -1 and 4 at t is equal to 0, and then we're moving in that direction towards this point, which is 4 and -3. And it doesn't say what time we have to be at that point. It just says that we start here, we're here when t is equal to 0, and then we move that way. We move towards this one, okay? And I guess like there should be one more bit of fine print along a linear path. Okay, so say there's a one extra detail that, yes, the path that you're moving along, the way that you're getting from here to there is along a straight line, okay? So a consistently linear path. So how would we do that? Well, here's what I think is a fairly easy procedure to get this together. I just note that there's a certain amount of movement up and down and left and right to get from here to there. And the reason why I think of it that way is because parametric equations separately track the x and the y from t. So like if something's moving, its horizontal position changes according to this. And y, its vertical position changes according to that. Now they change together, but maybe it's moving up more than it's moving to the right or something like that. But all this does is separately track its x and y movements as functions of time. So I thought, why not do this? Let's actually describe what happens. How do you get from here to there in terms of vertical and horizontal movement? Well, this point's at 4 and that point's at -3. So I would say that you go down 7, okay? I mean, you have to, like one way or another. That's how you're getting from here towards there. And then you'd have to go, well, so that point's left 1 and this point's right 4. So we'd have to go right 5 to get from here to there, okay? And I think that's all you need to know to get parametric equations of this situation. We can say x and y equals this. Put some constants here that represent where you want to be when t is equal to 0. -1 for x, 4 for y. And then horizontally, we're moving right 5. So say plus 5t. Start at -1 for x, move right 5. That's how you can read that. And for y, start at 4 and move down 7. So for y, start at -4, then move down 7. Okay? So this will do it. So try it. Where are you? So say we're going to test this out. We're going to make sure this is right. Where are you when t is equal to 0, according to these equations? Well, your x-coordinate's -1 plus 5 times 0. That's -1. And your y-coordinate is 4 minus 7 times 0. That's 4. So that part checks out, because we wanted to start at -1, 4 when t was 0. And where will you be when t is 1? Let's try. So when t is 1, so put 1 in right there. What's negative 1 plus 5t? That's 4. And then what's 4 minus 7? That's negative 3. And so that would take you from here at t is 0 to here at t is 1. So yes, these are parametric equations for an object that starts here and then moves in that direction, getting at that point at time t is equal to 1. So this will do it. It's not the only way to do this problem, and this is not the only answer. Okay? If I had done this differently, I could have put it at that point at time t is equal to 2, or any other time that you can imagine. But like this at least allows you to track movement along a line. Decide where you're starting, decide your left and right, up and down movements, and put it together that way. Okay? All right, and is this a linear path? Well, if you find the path, if you eliminate t, yes, the path for this will be y equals mx plus b of some kind. It will be linear. All right, and you can prove that in the way that we've done some other problems. So, okay, let's try then something that is maybe like one step removed from the one that we just did up there. Consider this one. Give parametric equations for the object moving along this line, starting at that point when t is equal to 0. Okay, now this is just a line. Somehow I need to incorporate time into it. Like this other one. I have equations that put you here at time t is 0 and here at time t is 1 with motion otherwise in a straight line. Okay? So I want to do something like that with this one. I think we could do it the same way. Okay? So let's try it out. Here's a rough sketch just to help me explain it. So you're like, right there. Negative 2 and 9. And that's when t is equal to 0. And you want to move along that exact linear path. Okay? You've got to move along that. It's just that we want to be at this point at that time. That's the only condition. Okay? So, why can't we just find another point on this line and do it like the one I just did up there? We could do it like that. There's nothing wrong with that. What is another point on this line? I mean, there's lots of points to choose from. You just need another one. Why don't we choose the y-intercept? Okay, so here's the y-axis. Where does this hit the y-axis? Hits the y-axis at 1, so maybe like that. Okay, so let's say we're moving to the point 0 and 1. All right, so yes, there would be motion along this line. I'm going to put you here at t is equal to 0 and there at t is equal to 1. How do we say that you do this in that last example? You just break this down into vertical and horizontal movement. If you're moving on this line between these points, then you would go down and to the right. How much? Well, you start vertically at 9 and you move down to 1. That would be movement down by 8. And you start horizontally at negative 2 and you move to 0. That'd be right at 2. Okay? So how do I say we do the other one? X and y. Where are we starting? Where must we begin when t is equal to 0? We have to start where x is negative 2 and y is 9. But we move right 2. So x will be negative 2 plus 2t. And we move down 8, so y will be 9 minus 8t. Those equations will put you here at t is equal to 0 and here at t is equal to 1. Okay? And those are points along that line. So every condition in the problem is satisfied. These parametric equations have this path because my points come from that line. And they definitely put you here at t is equal to 0. So everything given in that question is satisfied by those. Okay. Now, so somebody could say, like, that there's this is too open-ended. Like, why did I choose this point? I could have chosen lots of other points, right? Why did I choose this one? Well, so really there were no specifications given in the question. So there are lots of other ways I could have done this, all right? But my point for you to see is that this satisfies everything that's there, all right? Now, so sure, there are lots of other answers. I thought we'd discuss a few of them, all right? So say we got this one answered. That is the answer to what you have up there. But let's talk about some differences. So say I think about the same question. Give parametric equations for something moving along that line, y equals 1 minus 4x, at this point right there when t is equal to 0. That's the exact question I was just talking about. Here's one answer, right? That's the answer that I gave. There's more than one answer. This is one of them. I just did it. And yes, I said it will put you there at t is equal to 0, as is indicated. And it will put you here at t is equal to 1. Okay? But, you know, I could have chosen that point out there and gotten a totally different answer. So here's another answer I could have gotten if I had done it slightly differently with some other point. Okay? This answer does, you know, still answers the question. It's got the same path. Y is 1 minus 4x. But it puts you at this other point way over here when t is 1. It will put you here at t is equal to 0 at negative 2 and 9. It will put you here at negative 6 and 25 when t is equal to 1. Okay? All right, so both of these could be answers to this question because they satisfy the path and the point at time t is equal to 0. So let's think about this. What's the difference between them? Okay? I mean, they're not literally the same answer. They're both answers to that question up there. But these are different. And the difference is in the speed and the direction. Okay? This one moves you to the right along the line. This one moves you to the left. Okay? Another thing, I would say that the motion is faster on this one. Okay? You can get from here to there in 1 second according to these equations. If, let's say, seconds are your unit of time. But on this one, that point is a lot further from this one. That's a further distance than this. But the time is the same. You can get from here to there in 1 second. So the difference between these, although they both count as answers to that question, is in their speed and the direction. This one is faster. Okay? This one is slower. This one is motion to the right. This one's motion to the left. Other than that, they do the same thing. Okay? All right, so that's how that last question can have 2 answers to it, or 3 answers, or as many answers as you want. And there's a little bit of an explanation of the difference between them.